We're now going to turn our attention to what is known as the electric field, which is a very fundamental concept in electricity and magnetism. And in fact, the idea of a field itself is fundamental to all of physics. Modern physics views fields as all there is, at least the quantum view, where particles and matter made up of particles are just excitations in some underlying field, but that field could be considered more fundamental than the actual matter itself. So moving right along, looking at the electric field and continuing to draw on our analogy with the gravitational field, we know that the gravitational force is equal to the mass of an object times the gravitational field strength. And if we rearrange this and solve for g, we get that the field strength is defined as the force per unit mass, the gravitational force felt by an object per unit mass. So our electric field, we're going to have an E instead of a G. It is a vector quantity, just like our gravitational field was. And it is the electric force rather than per unit mass. You guessed it, it's going to be per unit charge, which we use a Q for here. So if we rearrange things a bit, we can also solve for the electric force in terms of the charge times the electric field that the charge is in. Now we have another expression for the electric force, which was Coulomb's law, KQQ. Here I'm going to use lowercase q for the charge that we're interested in, and then uppercase Q for the charge that is responsible for the field. Let's look at it in terms of gravity, just because maybe will make a little bit more sense. So our gravitational force is G m over r squared over little m. So here we're talking about this big M typically is like the planet. So that's the mass that's predominantly responsible for the gravitational field you're interested in. But you have the other mass, and that's the mass we're interested in measuring the force of. So that mass goes away. Same idea here, where we have a larger charge that's producing an electric field, and then we're using a smaller charge to measure that electric field. And we call this smaller charge a test charge, and we're going to use this idea quite a bit. The idea is that the test charge is so much smaller than the other charge that's producing the field that the the electric field from this charge is negligible. So similar to the idea here, if you are using some kind of ball or something to measure the gravitational field strength, that ball probably isn't going to have a large enough gravitational field to change the gravitational field due to the planet very much. So same idea here, we're just using a small charge to test the field due to the large charge. So this gives us KQ over r squared, and it would make sense that the field due to this charge Q doesn't depend on the other charge that you are using to measure it, just like gravitationally. And this is an equation we saw a while back. That should be a big M. Sorry. Gm over r squared. This was the way to find the gravitational field strength or the gravitational acceleration on the surface of any planet, as long as you know its mass and its radius. So similar idea here for the electric field. So the idea with this field is it's the we just said it's the force per unit charge. So one way to find that field is we could put this test charge in different locations and find the force. So maybe here there's a large force on it, here we're a little bit farther, so it's a little bit smaller, here we're farther still. So that will not only tell us the strength of the force, but it will also tell us the direction, and that's how we also define the field. It's a vector field, so it has a given magnitude and direction. And all we would have to do is divide these by Q, and these would become the electric field. So the proportions would remain constant because we would divide by a constant factor. Another way to look at it, if we know that the electric field at this given location is indicated by this vector, well, the force is going to be in that direction. Its magnitude is not going to be exactly the same, but it will be in that direction. Oh, I should also mention that by convention, the electric field, so E, points in the direction of force on a positive charge. So with gravitational forces, we didn't have positive and negative mass, so we didn't really have to worry about this little correction here. But with the electric field, we have to choose the field to be pointing in the direction of the force on one or the other, and we choose the positive charge. So the electric field is still pointing in this direction for this negative charge, even though the force, if these charges are of equal magnitude, these forces will be of equal magnitudes, but the directions will be opposite. So the electric field tells you the direction opposite of the force exerted on a negative charge. And because it's a vector quantity, you can just sum the fields due to more than one charge. If both of these charges are significant, we don't have a teeny little test charge that's contributing a negligible field. Well, if I want to know the electric field at point P due to both of these charges, well, I could calculate the electric field due to charge 1, and it would be to the left because this is a negative charge. So a positive charge would be attracted. So this is my positive test charge sitting here. It's going to be attracted to that negative, so it's going to feel a force that way. So we would say that the field is to the left. Now we've got a positive charge over here, which is going to be a smaller field because that distance is larger and we still have an inverse square relationship. But this is a positive charge, so it would be repelling this positive charge. So both of these fields would be going to the left, and you could solve for those pretty readily just by plugging in KQ over R squared for each of those, and then add them together would give you the total field at that location. Now if you have a little bit more complicated situation, I'm not going to do calculations here, but if we have these two charges and we want to know the field at a location not on the line between the two charges, I guess these charges are a little bit different anyway, but anyway, at some points out here, we again just have to sum those fields, but we're going to have to deal with vector components and all of that fun stuff. So a positive charge right here is going to be repelled by this positive charge, so that is the field at location B due to charge Q2. Now this is going to be a negative charge, so it's going to attract a positive charge, so that field would be there, and you would sum those two fields. The vertical components would cancel, and you just have a horizontal component. So this is the total electric field at point B. Over here at point A, where you're in line with Q2 here, it's going to have an upward field away from the charge. This field is going to be down and toward that charge, so right there the field is going to be going this way. And you could find the field at any point in space. There's not like gaps in the field. There are fields everywhere at every point in space. Let's do a little example of how we could calculate this. So this is one way that a copy machine works. I'm sure there's other designs of copy machines. But one way is to have a drum, and you have an electric field on that drum, and then when you put the toner on there, it will line up according to that electric field. Nice big giant letter A here. And if we want to find the electric field necessary on that surface of that drum in order to keep these toner particles, each with a little bit of mass, and we're going to say that each toner particle has to be charged as well, otherwise it won't be affected by the electric field. So they each have 20 extra electrons, so we can get the charge from that. And we're going to assume that the electric force is twice its weight, just to make sure that when it's upside down it doesn't fall off. So if the electric force is 2 times the gravitational force, the electric force is given by Q times the electric field. Electric field is what we're going to solve for. That's 2 times mg. We're assuming we're on Earth, so this is just going to be 9.8. We're going to solve this equation for E, 2 mg over Q, and we're mostly done. Now we just have to plug in some numbers. The mass is 9 times 10 to the negative 16th. G is going to be 9.8, and Q is going to be 20 times the charge of an electron, and that is the elementary charge. We'll just round that to 1.6 times 10 to the negative 19th, and that works out to be 5.5 times 10 to the third, not fifth, 10 to the third. And the units, as we mentioned earlier, it's the force per unit charge. So units of force are newtons, units of charge are coulombs. So one of the units of the electric field is the Newton per Coulomb. So if we look here at two charges, this one here is a positive charge and this one is a negative charge. So these are the electric field at different locations. They would be going in towards this charge and away from this charge. And if we move this around, it's going to change our electric field a bit. But it's kind of a pain to have to draw arrows all over the place to define the electric field at all these different locations. And in fact, the electric field is in all these gaps too. We can increase the number of arrows drawn on this applet and so forth to get a nice muddled picture like this, where we've got a bunch of arrows all over the place and there's still gaps, so we're not fully describing the electric field. So we use kind of a shorthand notation of what we call the electric field lines. So field lines look like this, nice and neat. And all we do is draw lines coming out of positive charges and going into negative charges, because that indicates the direction of the electric field. And then if the field lines are closer together, like they are near the charge, then that indicates that the field is stronger. Where the lines are farther apart, the field is weaker. Also, the number of lines you draw is proportional. I'm going to summarize all these rules at the end, by the way, so you don't need to write them down yet. The number of lines you draw is proportional to the magnitude of the charge. So these two charges are equal in magnitude, so we draw an equal number of field lines all around it. And these charges are considered separate situations. I don't have two charges next to each other. If I do have two charges next to each other, I get a picture that looks more like this, where the lines going out of one will go into this one, and you can get these nice curved shapes. So what the field lines tell us, if we look at a point on any field line, the line tangent to that curve is the direction of the electric field at that location. So we can still get an idea of what's going on with the electric field without having to draw a bunch of dots and arrows all over the place. Here the electric field would be going directly to the right. And we can also see where they're bunched close together, the field is stronger. Where their field lines are farther apart, we know that the field is weaker. Here are some other configurations. As I mentioned earlier, the number of lines correlates to the size, the magnitude of the charge. So if this positive charge here is twice as large as this negative charge, then I'm going to have twice as many lines coming out of it. Now, not all of them are going to connect back here. They'll just kind of go off in space. You can have positive charges like this, where you're going to have a lot of cancellation going on in the middle region here. And here's one other situation we're going to look at a lot later when we get into capacitors. If you have two charged plates, then the field lines basically go from one directly to the other. And in the middle here, you'd say you have a uniform electric field, which is a lot nicer for analyzing than curving things like this. You do have what we call fringing effects around the edges, but guess what? We're typically going to ignore those, and we can get some more complicated situations. Let me show you some other fun things. So here I've got a different applet. Here I can select the magnitude and the sign on my charge. So if I put a positive 2 charge, I'm just going to have field lines going directly out from it. I'll do another positive charge, 3 this time, and we can throw a negative charge in here. Let's go -1. Anyway, you can get all kinds of shapes like this. For your field lines, if we hit randomize, it's going to give us all kinds of crazy complicated situations, but these field lines will still give us a general idea of what the electric field is looking like, which is telling us about the forces that charged particles would feel in vicinity of these other charges. Now, in this case, we're assuming that either time is stopped or these charges are somehow fixed, because these charges would be exerting forces on each other as well, and they would start moving around if they were free to do so. Alright, so just summarizing how to deal with field lines. They indicate the direction of the field, obviously, and the field is tangent to the line. The magnitude is proportional to the density of the field lines, so it's closer lines to more lines together. They're densely packed. That means it's a stronger field. They start on positive charges, end on negative charges, so if you ever have a positive, the field lines need to go out from that positive charge, however many you draw, and negative charges, they need to go into them. And the number of lines is proportional to the magnitude of the charge, and that's all there is. See you next time.